All right, how we doing, everybody? Doing good? Tired? Sleepy? I know, me too. Anyways, today I want to talk about it's welcome back from the spring break. Okay, I already met a few of you guys earlier, so. But yeah, I didn't assign anything over to spring break because I'm a believer that everyone, go get some sleep. Okay, you guys worked really hard. You guys are doing great in your other classes, so congratulations. We're already halfway there, right? Are we halfway through the semester? Are we? I think so. I don't even know. When's the drop date? I'm not just saying that for funny. March 31st? April 1st? I don't remember either. But anyways, for this lab, I think we're already halfway there because I have the 3 assignments. I'll get grading the 3rd assignment very soon. Yes, I've also been on vacation too because the director needs to sleep. But I think I'll make an assignment 4. It's probably going to be simple, easy. Just talk to me about Current Mirros. Does that sound fair? Then assignment 5 is probably going to be just do some simple amplifier. Because we're going to talk really fundamentals because I've already done a poll already, okay, for those watching from home. But yeah, 420 knowledge is okay, not okay. No? Okay, let's just talk about it again now that everything's recording. Let's see, boom, boom, boom. This is what you guys learned. When did you guys learn this? So did he start this PowerPoint, this right here yesterday?
No, it was like
Last week? Wednesday? Before spring break? Okay. Let me see. So yeah, because you learned about poles, you learned about CS amplifiers, stuff like that, right? But honestly, I don't want to talk about that because I need you guys knowing what this guy is right here, which is the current mirrors. Right? Current mirrors. I want everyone to know this right here. By the end of this class today, this is your homework. Does that sound fair? What do you guys think? Sound like a fair assignment? Yeah, just study the PMOS current mirror and the NMOS current mirror. Because honestly, I need you guys learning your. Did he make you do simulations? No. Oh, okay. I wish I wasn't recording because I could go on a rant. Let me see if I can do something funny. No, I can't pause it. It's okay. So, how are you verifying your homeworks? ChatGPT? That's okay. That's fine. Be honest with me, okay? He's not using Spice. He's not even using Virtuoso. Huh? ChatGPT? Not even from the instructor manual book with text. Good job, y'all. It's okay. So you're not even using Spice on this, right? I'm gonna turn this into a more important lecture because I need everyone to take this home. Okay, I want everyone to take this knowledge home. Everyone in the class. Okay, I want you guys knowing how to do op amps. All right, or just how to use these transistors. We're getting to cadence. Okay. But I want everyone to know that you can do transistors at home, okay? Is that fair? Because once you guys leave this course, I think you still have until May 30 to play with cadence, right? And then after that, boom, it disappears unless you research with me and join whoever's going to be Dr. Baker's replacement upstairs. So this is very important to know. So let me just do... If you go to LT Spice, everyone has LT Spice. And we go to... LT Spice. Let me get an NMOS. Okay, NMOS 4. Okay, I'm just going to show you this because I need everyone to know what's going on. This right here is your transistor. PMOS 4. Grab PMOS 4, okay? And I'm going to do this because I have OCPD, okay? So originally, I'm going to click on this, okay? NMOS 4, right? You see the arrow, right? You see the gate, okay? Look at the PMOS. I just flipped around, okay? But me, if I were to stamp this like this, right? Personally, I'm gonna get confused, okay? For just me, okay? The way Dr. Baker taught me was just do was it Control R twice and press E, right? And boom, now I can differentiate from stuff, okay? Okay? If I were teaching 320, this is the first thing we do the first couple weeks, okay? I'm how did everyone take Dr. Zai for 320? Or who'd you guys take for 320? Online, Wenshen? Son? Did anyone use LT Spice with them? Okay. That's good. That's good to know. Thank you. Thank you. I understand why Dr. Baker does his things. Anyways, poor instruction. I wouldn't want to say that. I would say no instruction, or I don't know. Anyways, I think what I want everyone to try and do, and personally, okay, let's CMOSedu. You're gonna do this for your personal research, okay? I'm gonna click on R Jacob. No, not this one. Courses. I'm gonna click on 420. Okay, it's on recording. Let me see. Jeez, it's been a while. Right here. Is that cool? Oh, hey, I knew this guy. This guy graduated. He was the last doctor, PhD student for Dr. Baker. Great guy. Let me see. Let's go to course lecture notes. When do you learn MOSFETs? I'm going to show you. You're going to be sad. Let's see what the first week looked like. Did you guys learn this the first week? No? Actually,
barely touched diodes at all. This is
first week right here. Playing with transistors. Did you guys play with transistors the first week?
first week was.
No?
Yes.
What about second week?
Like injection fabrication or whatever. Like basic materials made of.
Let's see if I can show you something. Small signal model examples. Let me see. When did you learn this? In Dr. Ming Zhu's class. When did you guys learn this? Last week? A week ago?
Before the first midterm.
Right before the first midterm. When did you guys learn basic current mirrors? Last week. And look what lecture we're in right here. This is week 1, week 2, week 3, week 4. So right into week 4. And we're already on week 9. Right? Okay, we're going to click on the basic current meter right here. Or what's it called? Basic current mirror. But does he give me files? I don't think he does give me files. No, let me just go check. Where can I download his book? Homework assignments? There it is. Not the C5. Should I use the C5 models? Should I? Okay, let me just do something funny. Okay, I'm gonna go to right here, right? I'm gonna go up. Okay, whatever. I'm gonna click here, and maybe I'm gonna make you guys do this for your personal research. Okay, go to your root directory. Okay, go to share. Go to apps. Go to cadence. Go to libs. Is this it? Free PDK. Is that the C5 process? I don't think that's a C5. CDNS. Let me just click on this. On semiconductor. Oh wow, they changed. Where is his homework book? Let me. Okay, click on this link right here. Sorry, I'm just blanking out. Okay, click on this folder, right? I'm gonna open this folder, right? I'm gonna Control Z or Control X. I'm gonna go to 420. I'm gonna click on New. I'm gonna put folder LT Spice Work Okay, I'm just going to put this in my folder right here. I'm going to throw that there. Extract all, extract here. Yes. Okay, I'm going to click on this. C5 models, CMOSedu models. And let me just check. Let me see. What lecture did he do it in? Lecture, course, because I need everyone to know this right now. Lecture. Sorry, I'm blanking out. Lecture 7. So let me click on lecture 7. Right? Is that cool with everybody? So I'm just, what you want to know why I opened that right there? So I can just copy paste it right here. Is that cool with everybody? So I have this new file right here, right? I'm going to do file, save as. I'm going to call this one wrong folder. Boom. LT Spice work. I'm going to call this one, I don't know, learning. Okay, I'm just learning, okay? I call this one Current Mirros. Okay, I'm just going to learn Current Mirros, okay? So what I'm going to do is I'm going to go steal this CMOSedu file, okay? Control C. Back out of this. Oh, back out of it. I'm going to put it in my learning folder, okay? Right? Right, Dave? Yeah, you got it, right? And what I'm going to do is I'm going to do the following. You see this right here? Press period. Press dot include CMOSedu underscore models dot text, right? You know what that does? Boom. Gives you the models, right? What's the model that I have? 1 micron model. I have a 1 micron PMOS. I have a 50 nanometer process. That's a lot. And a 50 nanometer process for the PMOS. See all these parameters? That's all. This is like Dr. Baker made this process. He invented it, okay? Super smart guy. So smart. Yeah, you see, look at this. He calculated all this, okay? And then he put it into a text file so you can start researching, okay? So that's what that is. So I'm going to right-click on this, and I'm going to type in, I'm going to do 10U. Length is going to be 2U, okay? And then let me just go to, right-click on this NMOS, and I'm going to call it N underscore U1 or 1U, right? Okay. Press G for ground. Boom. Right, ground. Okay. I wonder how much education I should give you. Anyways. We should redo lab 1, right? Recreate how we did lab 1, remember? Remember that lab 1 stuff? What did I do? Voltage source, right? Right? Boom, like this, stuff like this. I'm just going over fundamentals. Okay? I'm going to do another voltage source right here, right? Because I don't know what this process is, correct? You're going to do this at your AMD interview when you get the first job, right? I'm going to call this one VGS, right? Everyone's going to do this when they work at Apple. VDS, right? I'm going to put this at, I'm going to hold this at 1 volt or 0 volts, okay? And let me just also hold this at 0 volts for now, okay? And then I'm going to do labels. N for labels. VGS, right? Click here. VDS. Is that cool, right? And then I'm going to go to, and then let me just turn this off. I'm going to go to run, right? I'm going to perform a DC sweep, right? We're going to do this at the interview. My source to sweep, ID versus VGS, right? Stepping VDS, remember that assignment, right? So I'm going to sweep VGS, right? So what's the source I'm going to sweep? VGS, right? Type of sweep, linear, right? Start value from 0 to, I don't know, 5 volts in 1 millivolt increments. Is that cool? Oh, I don't want to do that. Anyways. Boom, is that cool? Well, what's going to happen with what's ID? The current right here, right? Everyone agree? Click on it. Why is it 0? Because of this guy, right? I didn't put anything in there, okay? So I'm going to show you something cool. Let me see. I think it's this. VDS. If you put this in... Oh. What are you talking about? Anyways. I'm going to do something called step param. So the step function, step, right? Param, or step param. VDS, right? From 0 to 5 in 1 volt increments. Is that cool with everybody? Run. Hello? What the heck? Step param. Let me see what it does. Let's see. Start value, stop value, increments. Sorry. You have to also call this one VDS. There we go. There we go. Okay. Step parameter VDS, right? VDS, right? Okay, someone's getting confused with me. I don't know. David. Is that cool? No, I'm talking about me. Okay. Anyways, run it. Does that look cool? But why is it doing that? Let me see. Hold up. Because I'm trying to step this up. Oh! Let me see. Hold up. Give me a second. Let's see. How did Dr. Baker do this? Oh. Let me right-click on this. Control right-click. There we go. Let me see if I got something wrong here. Step parameter 0 to 5 in 1 volt increments. Oh, sorry. Okay, that's VGS, right? I'm going to click on here. There you go. That's what I wanted to see. I'm going to do the following. Add plot plane above. Boom. Remember that? Assignment 1? Am I wasting people's time? Is this good information to know? This is the first thing you're going to do when you go to Apple and they're going to throw you, I don't know, their secret, I don't know. Are they going 3 nanometer now for M6? My Apple M6 Pro Max? Right? But they're going to throw you something. And what's the first thing you're going to look at? Like what these curves are, okay? And what does this mean for me? See, I can go here and what's the on voltage, right? Around 800 or 900 millivolts, right? Is that cool with everybody? Let me see what Dr. Baker did. 5 volts, so okay, that makes sense. Let me go up here. Anyways. Cool sweep. Now let me do the following. I'm going to save this as current mirror, or what do you call it? This is actually going to be called the, I'm going to call this one the ID versus VGS stepping VDS, okay? That's what this is, okay? Control S, okay? Now I'm going to save it again, save as. ID versus VDS, right? Stepping VGS, correct? Right? Remember assignment 1? So I'm going to do the following. Wait a second. The heck did I do here? Oh yeah, there we go. Call this one 0 volts, okay? I'm going to call this one VGS, right? Okay? VGS, right? Run it. How's that looking like? Let me see. Get rid of this. And click on VDS. VGS. Let's see. stepping. Okay. Oh, sorry. I didn't change this one right here. We have to sweep VDS. There we go. Step VGS. There you go. Ah, that looks beautiful. How's that looking like? Looks cool, right? What's this line, top line right here? Let me see. Does it tell me? Okay, I'm gonna do something funny. Why is it not? If I control right click, look, this is for VGS at 5 volts, right? 5 volts, right? VGS is 5 volts. Yes? So we're sweeping VDS, right? What's the current what's the saturation current for when VGS is 5 volts? Where's it holding at? 2 milliamps? Is that cool? Am I teaching? Is everything like all the stuff I've taught you from the first week like making a lot of sense? You see, this is. I'm not trying to brag to myself, but okay, maybe I'll brag. Yes, I was under Dr. Baker, and he really taught me what's going on, and I want to make sure you guys get your educations well too. It's not just numbers, it's not just math. It's can you answer the question, or can you tell me why this is happening? What's going on? Stuff like that. Don't tell me 2 + 2 is 4, or just show me. Oh, I got 4 oranges, or I don't know. Is that cool with everybody? Okay, that's just a bare fundamental that I want to show everyone, okay? So, what I'm going to show you right now, go right here. Was it this one? There we go. Okay, so I'm going to save this, Control S, Control S. We create a new file. Actually, I'm going to go open that old file, okay? Current Mirros? What the heck? Anyways. Okay, the original current mirror, right? I'm going to create a current mirror. So let me do this. Anyone bothered if I do this? Boom, 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 boom. Should I just copy Dr. Baker's circuit? Control C. The heck? Where is it? Where is it? Come on. Right here. Oh, it won't let me copy from different things? Are you kidding me? Come on. Darn it. It's okay. I'm going to open it right here. Oh. Where is it? Ugh. Maybe I shouldn't have. E420. Lecture 7, exercise 1. Let's just copy paste it. Okay. I'm going to right click this right here. I'm going to do 2 micrometers, 10 micrometers width. Okay. I'm going to control right click on this. I'm going to double click on this. Okay. So I can see the length and the widths, right? Okay. I'm going to copy, Control C, or not Control C, Control C, click on this, Control E, right? Is this making sense with everybody right now? I'm going to do R for resistor, okay? And then I'm going to do voltage source right here, okay? I'm just copying what Dr. Baker did. Boom. Boom. Boom, boom. There we go. Then boom, 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 boom. Is that cool with everybody? 5 volts, right? Simple stuff. So let me just show you. 200K. And then I'm going to do labels. VDD, right? What am I going to label this? VGS, right? Why am I calling it VGS? What's this right here? This terminal right here is the gate, right? What's this right here? The source. So VGS is VG plus or VG minus VS. The voltage difference, the voltage drop from here to here is VGS. Yes? I'm looking at you, David. You're in front of me. I'm waiting for your head shakes.
I was wondering what's the behind the arrow? You know, the MOS.
Oh, right here? Oh.
Yeah,
Thank you. Yeah, I'm too lazy. Watch this. Control R. I can't control R. Are you kidding me? There you go.
No, I'm saying like, what's that supposed to be?
This one?
Yeah.
Oh, no, this is just a symbol for telling you that this is an NMOS.
So like behind it connects to something like ground's connected to it for some reason.
This right here?
Yeah. Like, I'm saying like if that's ground, like and the bottom one's source, the top one's drain.
Yeah.
What's the fourth or the
This-
third?
You mean this?
Yeah.
That's the body.
Okay.
Who didn't do their offline? Come on. You're making me worried, Dave. I'm talking to myself. Blank. Or I don't know. Tutorials. Not the layout. Schematic view. You mean this right here? Let me show you. Oh, because you're used to this. Right? Yeah? You're not used to the other symbol? No? Is it because no one taught you 320 BJT's transistors? No?
It's just like just plug and chug pretty much.
Everyone knows this is the body, right? Gate, source, drain, right? VGS, what does that mean? The voltage between, well, from the gate to the source, right? VGS, right? Run it. Control R or run. I'm going to run this for, oh, he did in .op. Okay, .op. Oh, run. .op. Right here. This is just doing a DC analysis, okay? You see my probe? Or actually, let me just run it again. What's the current going through R1? IR1? 2.17 E minus 5? Right? What does that mean? I don't know. Let me hover right here. See if it tells me. 21 microamps. You see that? You see the bottom right here? Actually, let me just do screenshot. See if anyone's paying attention. There we go. No, come on. 3-second delay. Boom. Okay. 1, 2, 3. Everyone seeing this right here? 21 micro. I got that from the bottom of the corner. Okay, is that making sense? 21 microamps, okay? So if I click on, let me just do a transient, okay? I don't like this. Transient, I'm gonna do it for 1 millisecond, okay? Run it. Get rid of this. Run it again. What's the current? 21 microamps. What about the current here? 21 microamps. Let's click on it. Oh yeah. Right? Is everyone understanding what's going on? Do you guys know how to change the width of these transistors? Right? If I go here, right? And I want to have twice the current, right? What am I going to do to the width? Double it, right? What are you going to see with the current? Here's M1, right? Where's that at? 43 micro, right? What if I want to times 10? So I'm going to do 10 width, right? I'm going to do 10 microns for the width, right? Do you see this parameter, right? Let me see. Number of parallel devices. Is that my multiplier? Let me see. I forgot how to do multipliers. Give me a second. I think this is right here. Let me do 10. I think that's correct. There we go. Four, 3, 4. Oh, okay. Sorry, I didn't change this right here. If I multiply it by 10, right? What's the current here again? 20, right? If I multiply that by 10, what should I see right here? The current. 200 micro, right? Is everyone understanding the bare fundamentals of current mirrors? This is what I'm going to expect for your cadence assignment, okay? All right, fair assignment? Because I want everyone to go home knowing like, hey, I've simulated a current mirror, okay? And better yet, I'm gonna make you guys lay it out too, okay? I'll give you that cadence experience, all right? Is that fair with everybody? Easy assignment. Let me see the other current mirror because let me show you. I'm not happy, y'all. I wish we can do a lot more stuff, but if your fundamentals are here, it's not your fault. Okay. Why did he do this? I think this was just another way of designing it? Question mark. Oh. Okay. I know what he did here. Let me just run it. Let's see. DC sweep. Do you guys understand what's going on here? Let me zoom in. Right? We're sweeping VDS, right? Right? It's the same current mirror we were playing with, right? Let me go back to the other LT Spice, okay? Okay, remember this right here? I'm gonna run it. No, not that one. Oh, get rid of this one. Where is my other LT Spice? Here it is. Okay, remember this? Right? Let me go back here. Okay. Multiplier 1. Okay. I get 20 micro going here, right? And I get 20 micro over here, right? Is that correct? That's a true current mirror, right? So what happens if this voltage is not 5 volts? It's like, I don't know, 4 or 3 or 2 or 1, right? That's what Baker does right here. Sorry, right there. So basically, look, at like 50 millivolts, right? We're getting like 10. You see, let me see if I can plot it right here. Can I do something? Plot settings. Can I draw? Let me see if I can draw a marker. Mark data point. What the heck? Whoa. Would it let me click on it? Plot settings. Mark data points. Reset colors. There's a way to like control. Oh. Let me see. Whoa. Control F. What the heck? Anyways. But yeah, you see as we get closer to, like, let's just say 250 millivolts, right? We finally get that current mirror working, right? And then let me see. This is obviously in saturation, right? It's holding that current. It's acting like a current. So we're making this 5 volts, right? Remember those IV versus VDS plots, right? And you saw it saturate. We're adding pressure at the water pump, right? Think of your house, right? And we're draining water, right? You're going to your sink, okay, right? And you turn on the sink, right? If I at the city council or like the water district, right? For some reason open Lake Mead and now there's like a flood of new water coming in, right? Do you think that's gonna, like, your faucet's gonna blow up or anything? Well, if it's weak, right? But let's assume it's strong, right? It's gonna hold at that current, right? 20 microamps, 20 liters per, I don't know, milliliters per second. Is that cool? Right? It's gonna hold no matter the pressure here at the water district. Everyone understand that? All right? So how much pressure do we actually need? Only like, let's just say 200 millivolts, right? So what does that tell you as an engineer? Oh, anything above 200 millivolts is a waste of money, right? No, not that. We're going to be designing amplifiers. You're going to be designing other current mirrors. This just gives you your space. In the bottom, you're doing these little current mirrors. On the top, you're also doing PMOS current mirrors. In the middle, you do your amplification, right? That's what you're going to be doing when you're being an analog design engineer, okay? You have 1 volt of space, or not 1 volt, 5 volts of spaces, right? 0 to VDD, right? At like 10% VDD, you're playing with like little things. At 90% VDD, you're doing other things. And between 10% and 90%, you're doing amplification. All right? I've seen all this in the industries and the works, okay? Anyways, let me click on this. Boom. Let me see if he shows you a PMOS. Let me see. Okay. Circuit 3. What the heck did he do here? Oh, he just multiplied it by 10. Exercise 4. And then he does the sweep. Exercise. And that was it. Anyways, I don't want to show you that one. You want to see this one? That's your 420 project. Should I make this your final project? I'll play. Nah. Here. Let's do some quiz time. What's this right here? Current mirror? What about this right here? Another current mirror, right? Why did we put this resistor here? Did he tell you why we put this resistor here? It's so that we can change the VGS of this right here, so that we can actually use this as a current mirror and change this voltage right here to be whatever we want it to be, V bias N. It's a really powerful technique, and it's like the foundation of all your iPhones. It's really, really cool. And then he builds what's this right here? Just this device called? Source gate PMOS. It's in saturation. And then what is this right here? It's just a transistor, V bias N. But wait, where's this coming from? It's coming from here, right? This is a current mirror, right? And this voltage right here, right? You see that voltage? I'm going to click on, how do I highlight net? View, edit, highlight net. How do I highlight net? Right click, highlight net. Ah, that's a terrible color. See that right there? So that means this is also a current mirror, right? Based on this guy up here, right? You guys know how to do this, okay? So it's not, once you start understanding what's going on, the project's not that scary, okay? You're going to go into the industry, and Apple's already like 50-year anniversary coming up, right? So they developed their own technology, Intel too, Microsoft, and you're going to come in, a senior engineer is going to be like, can you translate this? Don't be scared. Go piece by piece, okay? And then honestly, this is all bias circuits. This is a cascoding NMOS right here. Do you know how to do cascode NMOSs? No?
Barely touched that.
Okay, that's not good. But yeah, this is all just current mirrors. If you think about it, you see this right here, V bias 1, all this right here, this is all current mirrors coming from this guy right here and something else. Does that make sense? Let me see if I can get out of there. Okay. And then this right here is the stuff you're going over right now, I think, right? Lecture 12. Right? When was lecture 12? Let me see. Lecture 12. Cascoding the current mirror. And then guess what? That's all for your midterm. Current mirrors, cascodes. So that big circuit you saw is on your midterm. You guys miss Baker? I do too. And then look, Miller's theorem, common source, common drain amplifiers, two source amplifiers, stuff like that. OTAs. Anyways. Let me show you something else. Let me see if he does. I don't think he does it for you. Well, let me see. Should I do the PMOS version? I think I should. Get over here. I'm going to save this as current mirrors PMOS. Okay. What am I going to do here? Delete this. Delete that. Boom. Delete, delete, delete. Okay. So I can start from scratch. And then what am I going to do here? I'm going to do P for parts, PMOS 4, Control R, Control R. Let's put this, I deleted it. PMOS 4, Control E, boom, Control E, delete this, it's okay. Delete, boom, oh, boom, boom. Connect the gates, right? Connect this right here, right? Put the resistor right here. There you go. And then delete, boom, delete, boom. Is anyone bothered by this? The body, right? Goes to the VDD. Is that correct with everybody? Body goes right there, right? What's wrong with this? You got a source drain or a gate source connected, right? Or a gate drain. Like this. Is that better? Easy stuff? Okay. What am I going to make this resistor? I'm going to make it, I don't know, 200K. Right? And then what am I going to make this voltage right here? VGS. No, VSG. Source to gate. I don't want to do that. I'm just going to call it VG. Okay. And I think that's good. Run it. What's the current going through here? Let me get rid of this. Boom, boom. What's the current going through here? 18 micron. Let me just check one thing. I forgot to put my thing. 2 micro. And I'm gonna do something weird, but bear with me. There we go. Control R or control right click. Double click here. Okay. Control right click. No, click here. 2U, 20U. Okay. Control right click. Double click here. There you go. Okay. Because something that Dr. Baker did Dr. Zhu talk about the what do you call it, I think it's like the charge or the electron what do you call it, velocity of a transistor, I forget what it's called, the transconductance parameter for the PMOS is a lot slower or something like that, so you need to double the size of the PMOS. So your PMOSs have to be double because the PMOSs are good at moving holes, and holes are like these big, like there's electrons and there's holes, right? Positive charge and negative charges, right? Electrons, they just move fast, right? And NMOSs are great at processing that. PMOSs are good at processing holes, okay? So, but the holes are pretty big and they're pretty slow. So for NMOSs and PMOSs, the ratio from PMOS to NMOS is usually like 2-to-1. I've seen other ratios where it's like 5-to-1. So you have to multiply the PMOS by 5 or 3, and then the NMOS is your root. Okay, so 10 micron. Okay, so let me see. Is that what Dr. Baker did? Let me see. Let me see. Click on this one. Let me see, because he did 10 over here. What did he do here? I don't think he shows you. I'll be very sad if he doesn't show you. It's okay. He's worked too hard. Anyways, I'm just going to run it. Is that cool with everybody? 20U, right? What about the, let me see, open? Current mirrors? What the heck? Where is my, oh, did it overwrite it? No. No. Did it overwrite it? Let me see. I forgot to save it. Great. Save, everybody. Okay. I'm going to do this. Control, save as NMOS. Okay. And then I'm going to do, let me see. I don't like doing extra work, y'all. There we go. Boom, boom, boom. There we go. P, NMOS 4, okay. Oh, come on. There you go. And did I delete the text? Oh, I did delete the text. Whoopsie daisy. There it is. PMOS. Oh, what the heck? Oh, whoops. Dave. Not feeling it right now, everybody. Dot include CMOSedu dot underscore models dot text. Okay. N 1U 2U 10U. Is that cool? There we go. Right click. I'm too lazy. Delete. Control C. Boom. Boom. Someone's asking me why am I so good at this? Undergraduate studies. Yeah, undergrad does a lot to you. Click here. Click here. Click here. Boom. Following. Boom. 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 Is that cool with everybody? Final part. VGS, just for clarity. See this right here? Does that make sense right there? What's the current here? Something's wrong. Oh, something is wrong. It's supposed to be right here. There you go. VGS. And this right here is VDD. Okay. Oh. What's the voltage right there? 19. Right? 20. Let me see. Did I include it? .cd. Yep, there we go. That's fine. Okay. So I'm going to go back here. PMOSes. I'm going to copy paste this. Okay. Should have shown you this from the beginning. Oh my gosh. Control C. Boom. 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 There we go. And then I'm going to click on this one. P underscore 1U. This right here is going to be P underscore 1U, right? Run it. Am I right? What's that current right there? 18, 19 micron, right? For the PMOS, you see how it's 20 over 2, right? And then what about this one right here? Let me see. Why is it skewing like that? I don't know. Did I do something funny? Just S to stretch. S to stretch. Maybe it didn't like something here. Let me just click on this one. There we go. That's better. Close to 20 micron. Right? Is that cool? But you see how it's 10 over 2 for the NMOS, and for the PMOS is 20 over 2. This is important. This is going to correlate back to cadence. Okay? Any questions about the current mirrors? This is probably going to be your homework right here. Recreate this, but in cadence. Does that sound fair? And then times 10, or let's do times, like, just double it, make it easy. Okay, so you're gonna do this one, and do a layout for. You're gonna do this. Okay, you know what? I'm gonna start doing answers right now. Control save as NMOS times 5. Let's just times 5. Okay. What am I gonna do to this guy right here? Multiply it by 5. Right? And this is going to change this voltage right here because this is a gate source or gate drain connected transistor, right? What's going to happen to the current right here if I were to click on this? You see that current right there, right? Or actually, hold up. Sorry. It's not here. This is the one we're trying to buff. 5, right? Is that correct with everybody? If the current here is 20, right? 20 times 5, right? What's that going to equal? 100? Run it. Is that 100? That's what I'm going to want from your cadence homework, okay? Assignment 4, current mirrors, PMOS, NMOS. You're going to do 4 circuits, 4 layouts, 4 simulations. And the simulation's just going to be this. Show me this. That's it. Cool. And then what about this guy right here? I'm going to save. Save as x5, right? I'm going to multiply this by 5. This right here, Okay, let me be clear. This right here is a gate drain connected device, okay? Or gate drain connected. For the PMOS, right? Remember, David? This is the source of the PMOS. This is the gate. This is the drain. Remember that? Okay? Gate to drain connected, and this makes a saturation, right? And then I have this resistor right here, right? I'm gonna tell you this right now. This is the cheat answer for a lot of circuits, okay? This right here is like the reference, the reference of everything, okay? If you want to use this voltage right here to bias another transistor, that's what usually you would do. You would grab this transistor, and it's like a random transistor from far, far away. And this right here, let me show you what I'm gonna do. Right click, I'm gonna multiply this by 5. And this right here is your driver. Okay, you put this into a microcontroller, put this into like, I don't know, some amplifier or whatever you want. Does that make sense? So this side right here is like your reference, okay? It's very sensitive, it's very tiny, right? This right here is gonna be like your driver, like it's gonna drive a motor, it's gonna drive something big. Or your CPU driver, I don't know. Or the fan, you know the fans from your Intel boards when you build the PCs, right? That. Cool? Let me run this. What's the current over here? About 20, right? What's the current going to be here right here? I'm going to click on the top right here. 100. Is that cool? So that's what I'm going to want for your homework. So let me just Control S, get rid of that. Control S, give me that. And I'll give you guys those folder files too. So let's see how we can cheese this in Cadence before I go to my next class. Because I want to go home. Well, not go home. I have other things to teach. There we go. I'm going to go to My Library. You're going to do this for your homework. My Library. I'm going to create new cell view. I'm going to call this one my Current Mirror NMOS, right? Schematic. Okay, let's press I, GPDK, right? NMOS, what did we use? 1 volt? Yeah, let's use 1 volt. Okay. And then let me tell you another thing, and I'm gonna push this onto you guys a little bit, because I read the manual. Did you guys read the GPDK manual I uploaded? Was there one uploaded? Let me see. Just get rid of this right here. Let's see, dashboard. I'll promise to change that date. It's been ticking me off too. GPDK reference manual. Remember this? I'm gonna do Control F, NMOS 1V, right? What's the voltage for the the NMOS 1V transistor? 1.1, which means you get 100 millivolts of extra design space. Okay, so when you're doing your homeworks, change it to 1.1. Because have you guys seen weird numbers like 3.3 volts, 1.8 volts, or what's another one that you guys see? There's 5 volts, 12 volts, 14 volts, 42 volts, 48. There's like weird numbers, but for some reason in this process it's 1.1. Okay, because we're dealing with really tiny devices, and if you go too much in voltage, it's gonna pop. Okay, so yeah, you can use 1.1 volt. If you use 1 volt, that's fine, but use 1.1. Tell me how that works. Okay. Anyways, so that's what I wanted to show you there. Go back to Cadence. I love Cadence right here. Click. Okay, I'm gonna queue it. Should we do the smallest size because we're trying to be small, right? So yeah, let's do it there, okay? And then what am I gonna do right here? Actually, I'm gonna copy C. Is it Control E? No. And I'm gonna click here. I don't know how to Control E it. Can I flip it? How do I flip it? Oh, here. Rotate left. Flip horizontal. There you go. Is that cool with everybody? And then let me just do the following. Boom, boom. Double click there. Double click there. And then which one should be my thing right here? I'm going to put it right here. Is that cool? Right? And then what am I going to do here? I'm going to do the following. And yeah, I'll just do that right there. Okay. For transistor design, though, you're going to have to do something different where you're going to have to treat these bodies not like grounds, but sub, because that we're talking about the substrate, the P sub. So let me see if I can show you something cool. Let's go back to I. And what was that resistor we liked? Was it, let me just check the pieces. Was it res ns diff? I think that was the one we liked. And then let me just do calculate length. Can I do 10K? I can do 10K. Let me see. Let me see if there's another resistor here. SM Poly. I think I like this one. Calculate length. Let me see if I can do 50K or 100K. Okay, I like that better. Okay, let's try that. Okay. Is that cool with everybody? Then this right here. I don't like this. I think I'm just gonna kind of. How do we do that other assignment? Hold up, I'm getting PTSD right now. Tutorials. Was it my low pass filter? Schematic. Let me see how I did this. VSS. I think that's what I did. I'll connect that to VSS. Okay, so pin VSS. Oh, pin VSS as an input output. Okay. I'm gonna put this right here. Boom, boom. And then I'm gonna label this right here. Label VSS. Cool. What's the next pin? Sub. Input output. Cool. And what am I gonna label this right here? Sub. There we go. Is that cool with everybody? And then let me do the following. I'm gonna do label VSS just for fun, because that's how we DRC the thing. And I'm gonna call this one what do you call it? IREF, okay? And this is the current reference, right? Is that cool with everybody? And then you know what I'm gonna do? I'm gonna do another special pin just for fun, okay? I'm gonna call this one my V, what do you call it? V bias and okay. Let me right click on it. I don't like this. Cue it. I think he does it like this. V bias N. There we go. I like that better. Okay. Then what am I going to call this one right here? I'm going to call this one I out. I out. Is that looking cool? All right. Check and save. Woo! Homework 1. Let me just check. This is, yeah, we're just going to analyze this. Create. Cell view from cell view. Right? My library. Boom. Let me do the following. Let me see. So I want the top pin. Let's do top pins. Okay. I want these two to be on the bottom, okay? Because that's what I'm used to. Okay. I'm gonna put these two on the right, okay? Is that cool? And I'm gonna put this on the top just in case. I think I like that. Okay. Is that cool with everybody? And I'm just gonna check and save. Boom. Check and save. Boom. What am I gonna do next? Create a library or create a thing. Current Mirror NMOS, right? What am I gonna do? I'm gonna go to File, New, Cell View. The same name right here. I'm gonna do Sim, right? We're gonna simulate the piece. Press I. Go to my library, right? Go to my current mirror, right? Remember this? Is that cool with everybody? I'm noticing something. Maybe I should have redesigned this a little better. Just do this. Okay. So I'm going to add some components. I'm going to go to Analog Library. Okay, GND. Okay. Put this right here. Boom, 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 boom. Okay, is that cool with everybody? Yes? And then what I'm going to do, because I remember, I'm laughing at myself right now. We need to put this as a voltage, correct? Right? Voltage. So, oh, come on. Gosh, too many windows. Control E. Oh, where's my original one? Is it Shift-E? Control E. What the heck? Where's my sim? It's right here. Yes. What the heck? Man, my cadence is acting weird, y'all. Okay. I'm going to create a... Let's go back to Analog Lib. Let's instantiate... what was it? VDD? Right? Come on. VDC. There we go. And this is going to be 1.1 volts, right? Put this right here. Right? What is this going to be? I'm going to label this as I feel like there's another way to label it. VDD. Okay. And then I'm going to copy paste this right here. Oh. Copy. Paste. I don't like that. VDD. VDD. Boom. Boom. I'm going to copy paste this ground because why not? Okay. And then what is this going to be right here? Let me see. I don't like this. Anyway, so I'm going to move this right here. Because I just want to analyze this right here too. Call this one, I don't know. NMOS, okay. Okay. Then I'm going to copy paste this. Boom, boom, boom. Is that good with everybody? Check and save. Wait, oh. I'm going to just measure this for now. And then I think it's going to bark at me. Watch this. It didn't like that one. So I have to do I and go to library basic and type in nocon. Okay. I'm going to put this right there. I don't think it's going to like me there. There we go. Check and save. Boom. Cool. Is there everyone following? Not that bad, right? Easy assignment. All right. Launch. ADL. I'm going to do a setup. Because I want to do, I just want to do a transient. So let's do outputs to be plotted select on design. Okay, we have the magic wand, okay? I want to plot the currents. I'm going to press on I out and press on I ref, okay? I only want those, okay? Yeah, that's fine. And then I'm going to go here, analysis. Oh, wait, before you do that, press escape here. Okay, now it's gone, okay. Analyses, choose, transient. Let's do, should I do 1 millisecond? Yeah, 1 millisecond. Conservative. Okay it. And run it. Let's see what this outputs. 4.5 micro and 5.65. Is that okay? Let me see. Cue it. Yeah, okay. I'm gonna buff this. Let me see if I put this to do 50 ohms, okay? Check and save. Is that better? About 9 and 8. Is that cool with everybody? Let me do something even crazier. I'm going to go here. I'm going to do 10. Check and save. Press the play button. Dance. Hey, I like that. Is that cool? Is that a stable current? About 20 micron, right? I think you would tinker with this number right here. Go here. I think let's go with 15. I think 15 may be a ballpark number that we might have to choose. Play that. You see, this is what I do as a designer every day. Just play around and have fun. Yeah, I like that. Is that closer to what we do with Dr. Baker? Right? Is that cool? So what am I going to make you do for your homework? So you're going to create another block. Let me see. Okay. Who wants to do extra homework or extra work? No one wants to? I don't want to either, so do the following, okay? Save state. Save it, okay? Because I don't want to redo the home. I don't want to do this. My current sim, okay? Okay, now it's saved. Now you have to do extra work, okay? I don't want extra work. Work smarter, not harder. Exit out of there, okay? Exit out. What am I going to do to my, where is it? Current mirror NMOS. I'm going to copy it, right? I'm going to call this one X5, right? Current mirror NMOS and X5, right? Or should I do X3? Let's just do 5. Okay. What am I going to do right here? I'm going to go to the schematic, right? Right? This right here is my reference, right? This is my output, right? I'm going to cue this one. I'm going to put multiplier 5. Check and save. You're done. Am I an easy teacher, bad teacher, not caring enough teacher? Anyway, let me see. Check and save. Let me know. Okay. What am I going to do? The simulation. I'm going to copy it. I'm just going to add the thing right here, X5 at the end, right? You guys like it? You guys like this assignment? It's easy, huh? Okay. Click on here. Go to your schematic. Okay. What am I going to do to this current mirror right here? I'm going to replace it with the times 5, right? Okay. Boom. Launch the ADEL, but what did I just tell you guys? No extra homework. Make it easy on you. Go to load state, cell view, my current sim, right? Load it. Ignore that plot. Plot it again. Let's see if it gets 100. Because we did times 5, so 20 times 5 should be 100. Oh, yeah. This is our reference, right? I ref. What is this right here? I out. Half of the assignment done. Boom. Well, you have to lay it out. Should I make the assignment due in a week or 2? What do you guys think? 1 week or 2? Personally, next week is going to be a short week for me because I have something important to do next week in the Thursday. 2-week assignment, right? Lay it out. And then I'm going to end the video right here. You guys are going to research the PMOS, okay? 2 weeks to do this assignment. Is that fair with everybody? And if anyone's going to complain to me, it better be very soon. In terms of my cadence broke, something happened here, please let me know, okay? I'm going to get to grading your assignments later today. I have to do it very soon. But yeah, I'm happy you're using cadence now. And then I think there's another student. He's very happy too. So 2 weeks to do the assignment. Current mirrors, NMOS, PMOS, and then the ×5 versions. That simulation we see here, right? I'm going to include the LT Spice folders too. And the layouts, okay? You gotta make sure they DRC and LVS. If the resistor does something funny, let me know. Because how was the lab 3 with that resistor? Did everyone get the LVS? Right? Okay. Whatever resistor we use there, contact me and let me know because I hated it. Because it's a third resistors, right? 2 terminals, right? But why is there a third one? There's a third one because there's special other things. But I looked into the process. It doesn't need one. So let me know. Email me. Okay, 2 weeks to do the assignment. Friday, not next week, but the week after that, midnight. Is that good with everybody? All right. Have a good day, everyone.